time. And I can actually do that right now. I'll show you one little prop. Now imagine, okay, northern hemisphere is up top here. A little bit of atmosphere here. So I'll do my best. This is over to the lower right side of the building there. This is the northern hemispheric summer. That orientation, the sun and the ecliptic are high in the sky in the daytime. The ecliptic and all the planets are much lower in the sky. Now 6 months later, the sun there now. Oh, well, I did that backwards. Sorry, let's do that again. Okay, so recessional theory with some of the data, and I'm going to show you that it really does make sense what we see in the Observer's Handbook compared to what we would expect. I'm going to talk also about the consequences of recession from an observing point of view. Like someone new to observing, you just bought a telescope, I need to explain to you a little bit what you need to know so that you can, set up your telescope, right? And I'm going to talk about astronomical epochs and what they mean and how they apply to the changes that happen all the time with the positions of stars in the sky. A little bit about polar alignment. I'll give you one example, which thanks to Jay gave me a link that showed me one example set up. And then at this time we'll talk a little bit briefly about the other factors that affect precession, and well, not just precession but also affect the independence of the positions of the stars with respect to an observing perspective, because there's a lot of factors involved here. Okay, now I did show this one last time, and what I really wanted to show was the blue disc there is like the equatorial plane of the planet, and if you can imagine the same thing on a gyroscope here, the celestial spheres on the outside. If we imagine the wheel of gyroscope to be the like the celestial, the equatorial plane. Now with precession, remember we said last time, precession goes clockwise when we're looking down at the Earth from the northern hemisphere perspective. As the precession, and it takes nearly 26,000 years to do one cycle, you can see what happens to the equatorial plane. It sort of rotates around as well, which means that the equinoxes, where the equator and the ecliptic intersect, they will also rotate around like that, and that will make a big difference to the orientation of the stars, because if we use the RA and declination routine, as the vernal equinox shifts with that precession, so too will the RA and declination change as well. Okay, now this is the table I wanted to show you. Now down on the, I've got the right ascension and declination here for a bunch of stars. Most of those are in the bright stars that are listed in the Observer's Handbook, but some of them are not, because there was hardly, I wanted to get a reasonably good spectrum of right ascension from 0 hours all the way down to as close to 24 as I could get. But there's so few stars in the southern hemisphere, bright stars that are close to the South Pole, I really couldn't get really much information other than 22 hours of right ascension there. Now, fortunately, I had an old Observer's Handbook from 2010, and what I did, I made note of the coordinates for 2010 and for 2016 in our current, this year's and then what I did, I worked out what is the difference in declination over that 6-year period, and here's the difference in declination. That's right ascension there and declination. Now if we go back to that previous slide, what you'd expect is as the Earth starts to precess, you would expect the vernal equinox to also rotate clockwise around that celestial, or actually around the ecliptic here. And and that disk will sort of turn around as it goes. So you would expect that as the Earth precesses clockwise, you would expect, let's say this particular star here, as the vernal equinox shifts, you would expect the right ascension, which is measured in this direction here, you would expect the right ascension to increase as we go through time. Now with the declination it's a little bit more complicated because if you can imagine we're going up here, going down, then up again, if you sort of spun the thing, it would almost look like a sine wave. So where the line is rising here on that sine wave, you would expect the greatest difference in declination for stars that are round about 0 hour, and also the ones that are about 12 hours at the back there. Now any stars that are on this part of the sine wave, this part of the ecliptic, you wouldn't really expect much difference in declination round about hour 6 and hour 18 of the right ascension. So if we look at our numbers here, we find that I did do some calculations here to show what I thought was when I say expected, I mean this is for basically the ideal star near the equatorial plane. Sorry, near the equatorial plane. And you would expect about this number of minutes per year, or this much number of minutes over 6 years. And when I check these formula here, which are in the Observer's Handbook, they do actually work pretty good, for giving you a good approximation of where to expect to find a star. Oops, sorry. So, now we do notice that most of the difference is about 0.3, but because it's only one significant digit in the Observer's Handbook, it's kind of round-off errors here. So sometimes you'll see 0.2, occasionally 0.15, and I suspect there might be proper motion in the stars which are involved here, which will give you slightly different numbers. But notice Polaris here, 6.6, and the reason for that, if you can imagine a star that's just very, very close to the celestial North Pole, and then as the precession happens, that star now becomes on the opposite side of the pole. The right ascension is going to change by about 12 hours, over a short time. So that is why, like with Polaris there, with declination 89 degrees or more, it actually came up with a difference of about 6.6, because that close to the pole, that easy formula doesn't really work too well, because the right ascension lines are so tightly packed around the pole, so it doesn't take much to get big numbers there. But what I noticed too, and this is what I expected, remember I said that near hour 0 and hour 12, you would expect the greatest change in declination. Well, guess what? When we've got 0 hours, we've got about 2 minutes here. As we approach the 6-hour mark, it lessens, and then round about the 0 mark, roughly, or 6-hour mark, I should say, 6 hours of right ascension, we do have 0 change in the declination there. And as we go into the southern hemisphere, the numbers sort of in general start to go from -1 to -2, but then they're back to 0 again by roughly 18 hours. And as you're approaching the 24-hour mark again, the numbers start increasing a little bit and continue again up there. And the reason I did this, I wanted to satisfy myself that I understood what was going on here, because I can't explain to people what's going on if I don't really understand it myself. So I was quite happy to see that these numbers did work out pretty good, except there are a few anomalies, and again I suspect that proper motion or other things might be involved there. So, astronomical epochs. Basically, years ago we used to have, I think 1900 and 1950, we had tables set up where all of the star positions for the common stars and that were calculated exactly. What we can is perhaps use the most recent epoch. Yeah, these numbers are called epochs, and that's confusing too, because in geology, epoch is a period of time. In astronomy, the epoch is the beginning of a period. So you can use the 1900 tables for a few years after, but then when you get to starting getting close to 1950, you might be better off using those ones. And you might want to make further adjustments as well, according to this formula that I showed on the last slide there. Now, the convention for 2000 is that what's called the 2000 epoch is based on January 1st, half a day later at 12 hours terrestrial time, based on that Greenwich there, Zulu there. So all the tables and information that you get for 2000, and I think most astronomers have been using those since about 1984. But again, they're not totally accurate, they're only accurate on that particular date that's specified. Okay, I think we just covered that one, specify the epoch times. And as I said, if you're right between two of those epochs that you have information for, you can actually either extrapolate, or you can use those formulas to calculate how many years ahead of the epoch you're observing, and then you can get a more accurate RA and declination, assuming, of course, you're using those coordinates. Now, the only problem with that is that proper motion is the actual motion of the stars, which are all circulating around the center of the galaxy. They're all going at different speeds, according to how close they are. And then you've got the gravitational effects from the spiral arms, which are helping to draw more stars closer to those arms. So, without knowledge of the proper motions, there's going to be inaccuracies again. So, I mean, it's good to use whatever information you've got to find the exact position of the stars in the sky. Otherwise, when you take a time picture, then things aren't going to be quite right for you, or you're not going to find things properly. Now, things are a little better today. We're in the computer world now, modern generation. And with the Observer's Handbook, they list all the coordinates for all the common stars every year. So, for that year, and I think it's about the middle of each year, I think the Observer's Handbook of 2016, I think they're defined about so that gives you a pretty good idea of where you'd expect to find the stars in the sky. But even with people using computers now, there's all kinds of desktop planetarium software out there, I'm sure, where you can actually calculate, if you want to go and look for a certain galaxy or a star in the sky, a lot of these programs, they will just tell you on this particular date, this is what the coordinates, the RA and declination are. So things are a lot easier now for observing thanks to the computer revolution. Now, thanks to Jay, he sent me a link which showed how to align the scope with the celestial North Pole. Now, if we don't know precisely where the celestial North Pole is, and it's not exactly where Polaris is, then anytime you're taking a time-lapse photography, you're going to get a blurry image if the axis of your equatorial mount is not pointed exactly where it's supposed to point. And this is just one example for this Pasilla 4 telescope in the, whoops, sorry. Okay. Now this is what they call a reticle, which is a word I didn't even know before. But it shows you all different crosshairs and various things in the eyepiece, so you can help line up your scope. Now it's a little confusing because they've given you the Big Dipper and Cassiopeia here, and yet they're talking about Sigma Ursa Minor being down here, whereas we know, of course, that the Little Dipper curves down this way a little bit. But the only reason they show this is that if that is the way the sky is oriented, then this is what you'd expect to see in the scope where everything is inverted. Now, this time of year in the evening, of course, the Big Dipper is over this side of the sky, underneath the, just down this way from the... So it's almost the exact opposite. So if you were using that scope at this time of year in the evening, you'd have to look over here to find, Sigma Ursa Minor.
The crosshair rotation. You just turn it so Cassiopeia and the Big Dipper are in a approximate position.
Oh, they have them right there too.
Rotate the reticle.
Oh, okay. Yeah, okay, that makes it even easier then. Now what they've done, you can see that you line up Polaris within this line here, and then they've created epochs for 2005, 2010, 2020, and 30, and the star that you're looking for to align them here, this star, it shows the various positions where you would want to put it in that field of view there, so that you can get your alignment right. Now this OV Cepheus here is a very faint star, and they said that if you can find it, you know, there's very little difference here between the epochs until you get, say, between 2020 and 2030. But basically, it's a good technique to that shows you how to line up your scope. And I imagine that pretty well all modern telescopes now will have their own system of aligning things, and the more sophisticated scopes will actually have software. So all you probably have to do is type in your latitude and the date, and it will probably give you exactly, well, it won't even give you, it'll actually point your equatorial map right to the celestial North Pole. So things are a lot easier now to observe it, but it's still interesting just to know what goes into this. Eh? And you can see it close up here with Polaris. You can see right now Polaris is about halfway between the 2005 and 2030 epochs there. And the reason I showed this map here, this Sigma Ursa Minor is the second star, like we've got Polaris, and it's the next star, next bright star along this tail part of the Little Dipper there. So there's the star of interest there, and somewhere in this vicinity over here, I don't think it's that one because I think it's a fainter star, but somewhere over here is this OV Cepheus as well that you can see. And notice too, it says years increase in a counterclockwise direction in the reticle. And remember last time when I showed you, we know that the precession is going clockwise from the northern hemisphere, but if you look up, you know, in the sky, it's actually back to front. So they've got that part right. And here's an example of what it would look like in 2005, the various epochs, and 2010 on the right. And for 2020 and 2030, once again, you can see where they've got the star where this device is gradually creeping towards the celestial North Pole. And I think the closest point of approach is going to be about the year 2100, plus or minus a year or two. And it's expected to be within about 7 seconds of arc by then. So if you're still around by the year 2100, you may not even have to worry about aligning your scope. You can probably use Polaris and it'll probably suffice. Okay, for our folks in the southern hemisphere, or those who have the good fortune to go down there, it's a little more complicated, but the principles are the same. But as you can see, the reference stars there, they're much fainter, they're smaller dots, so it's going to be a little bit of extra work and trouble just trying to get things all set up for the southern hemisphere. But whatever software the modern telescopes have, or whatever kind of things they have in the reticle, it is doable if you go down there. Okay, now I showed this one last time too, and the only reason I showed it is because in the year 2000 you can see that the celestial North Pole was just down towards the Big Dipper from Polaris, and it's creeping ever more closely towards Polaris there. Now if we take a close-up look at the stars round about Polaris, now here you've got the Cepheus stars here. The ones which aren't mentioned all belong to Delta Ursa Minor, and you can see there's Polaris, there's the next bright star, the Delta one, which is known as Yildon, I guess it's commonly known as, and there's the OV Cepheus over this part. But I wanted to show here, it's got the actual celestial North Pole creeping slowly towards Polaris here. So I said by the year 2100 it's going to be pretty close to the North Star. So that'll be something to look forward to. Okay, see how we're doing for time. Okay, not too bad. Okay, now, it's not just the precession of the axis or equinoxes or equator, if you like, that cause star positions, movements. There's something which is known as nutation. Now these are very, very minor little wobbles in the Earth's axis, and the principal cycle on that is about 18.5 years. And the reason for that is because as you know, the plane of the moon will also rotate over an 18.5-year period, which is why if the full moon is very high in the sky one day, 9.5 years later the full moon will be a little lower in the sky. So that's another movement which has to be taken into account when all the ephemeris are calculated accurately. Another thing is what's called the tilt or the obliquity of the ecliptic. And the reason I show two of these is because, once again, it's so hard trying to find a nice picture online that's accurate. For instance, this one here says that the Earth's orbit tilts from 21.1 degrees to 24.5, whereas this one is the reality. It's actually about 22.1, I believe, to 24.5. But they both say that the current tilt is 23.5. It's actually closer to 23.4. And since the tilt is gradually decreasing at the moment, it won't take too much longer before the literature will all keep, say, 23.4, hopefully, because they just haven't caught on to that yet. But again, the whole period of that movement, increase in obliquity, that whole cycle is 41,000 years. So again, the effect is very small on what it has on the positions of the stars, but nevertheless, for accurate deep sky observing, it still needs to be taken into account. The other things which are of interest well is that the eccentricity of the Earth's orbit also changes over time, becoming more elliptical and then less elliptical. And the principal period there is about 100,000 years. And there's also a 413,000-year period as well. And you can see right now, even though we're sort of at a maximum, it's a very wimpy maximum compared to some of the other maximums that we've had in the eccentricity of the past day. And those three things together, the precession of the equinoxes or precession of the equator, the change in obliquity, and the change in eccentricity, they're what's known as the Milankovitch cycles, and they're very important when it comes to calculating accurate sky positions over time. But nowhere near as important as the shift caused by the precession. That is by far the biggest factor, and that is the one that should be of most interest, especially for beginning observers. Precession, the elliptic orbit around the Earth, which is the Sun, which is grossly exaggerated here, but it does actually rotate eventually very slowly over time, probably about 70,000 years or so that cycle is. Maybe it's even closer to 100, but it just shows you that the orbit of the Earth around the Sun and how you're going to view the stars is a little bit more complicated than what a lot of people have thought. Now, in the Observer's Handbook, they talk about the simple precession, and they also talk about something they call planetary precession or precession of the ecliptic. And I had to really scratch my head over that. But what on earth are they talking about? What do they mean the plane of the ecliptic is precessing? Precessing around what? Unfortunately, I found this nice diagram online which kind of explains it. There's something known as the invariable plane, which is not really completely invariable, but it's constant over for a general period of time. And all the planets are oriented a little bit off there. Jupiter's the closest. Mercury is tilted the most compared to that. And the Earth is tilted 1.6 degrees to this main invariable plane. So what they're talking about, the precession of the ecliptic there, or planetary precession, they're talking about the rotation of that, of this Earth disk here, this blue one. They're talking about the orientation of that with respect to that invariable plane. And it doesn't really explain that too well in the Observer's Handbook, so I thought it would be good at least to get an idea what they're talking about there. Okay, now do we have time for a quick video?
We have 2.5 minutes.
It's a 9-minute video.
Want to go from the time?
It's a really good one, and Chris will vouch for that. So this is really worth doing. Now, I've got to remember how to get to this now, Chris. Oh, escape, okay.
A human Earth is measured by one complete trip around the Sun.
Is it loud enough?
Seems simple enough, but there is a problem. The Earth doesn't travel in a path around the Sun that returns to its starting point. So how do we know when it returns? Well, one way, called a sidereal year, measures our orbit against the distant stars. As viewed from the Earth, our orbit causes the Sun to appear to move through the constellations of the zodiac on a path called the ecliptic. And when the Sun returns to its starting point, a sidereal year has passed. This motion is difficult to observe correctly because the stars cannot be seen when the Sun is in the sky. However, if you look at the sky before each dawn, the annual motion is very noticeable. The last stars seen to rise are not always the same, and within a week or two, an upward shift can be noted. As an example, in July in the northern hemisphere, Orion cannot be seen in the dawn sky, but in August, it becomes easily visible. Measuring a year this way is a period that is 365 days, 6 hours, 9 minutes, and 10 seconds long. Another possibility is to measure the year against the passing of the seasons. Because of the tilt of the Earth on its axis, the position of the Sun in the sky changes from day to day throughout the year. If we were to take a picture of the Sun at noon regularly throughout the year, we would see the Sun moving on this path, called an analemma. On the days in its orbit when the Earth is at a maximum tilt towards or away from the Sun, the length of the daylight is at a maximum or a minimum. These days are called solstices, and the Sun will be at the top left or bottom right of the analemma. On the days when the Earth's tilt is perfectly sideways to the Sun, the day and night are equal in length. These are the equinoxes, and the Sun will be at this crossover position in an analemma. When the Sun goes from one vernal equinox to the next, a tropical year has passed. Measuring this way gives a year that is 365 days, 5 minutes, and 4 seconds long. The length of the year on Earth is affected by several gradual and cyclical changes in its orbit and its tilt. First, there is the precession of the Earth's axis. Over a period of about 26,000 years, the Earth's axis traces out a circle in the sky. One result of this is that the North Star changes over time. Right now, the Earth's axis points towards Polaris. 5,000 years ago, the axis pointed to a star in the constellation Draco. And 12,000 years ago, the brilliant star Vega was the pole star. And because of the 26,000-year cycle, Vega will be the pole star again in 14,000 years. The precession of the equinoxes is caused primarily by gravitational forces of the Sun and the Moon acting on the Earth. While the axial tilt is the primary cause of seasons on the Earth, the distance from the Sun, which changes throughout the year because of the elliptical shape of the Earth's orbit, contributes a small bit of temperature variations throughout the year as well. When the axis is aligned so it points towards the Sun during perihelion, one hemisphere will have a greater difference between the seasons, while the other hemisphere will have milder seasons. The hemisphere, which is in summer at perihelion, will receive much of the corresponding increase in solar radiation. But that same hemisphere will be in winter at aphelion and have a colder winter. The other hemisphere will have a relatively warmer winter and cooler summer. When the Earth's axis is aligned such that aphelion and perihelion occur near the equinoxes, the northern and southern hemisphere will have similar contrast in the seasons. At present, perihelion occurs during the southern hemisphere's summer, and aphelion is reached during the southern winter. So the southern hemisphere seasons are somewhat more extreme than the northern hemisphere seasons when other factors are equal. In addition, other planets cause the ellipse of our orbit to slowly spin around the sun. It takes about 112,000 years for the ellipse to revolve once, relative to fixed stars. When considered together, the two forms of precession add, and it takes about 21,000 years for the solstice to go from aphelion to aphelion. The dates of the perihelion and the aphelion advance each year on this cycle, an average of 1 day for 58 years. The eccentricity of the Earth's orbit is a measure of how round or how oval the orbit's shape is. Over thousands of years, the eccentricity of the Earth's orbit varies as a result of gravitational attractions among the planets, primarily Jupiter and Saturn. The orbital eccentricity cycles with a period of roughly 100,000 years. As the eccentricity of the orbit evolves, the semi-major axis of the orbital ellipse remains unchanged, so the length of the sidereal year remains unchanged. As the Earth travels in its orbit, the duration of seasons depends on the eccentricity of the orbit. When the orbital eccentricity is extreme, the seasons that occur on the far side of the orbit are substantially longer in duration. In addition to axial precession, there is the axial tilt, the angle the Earth's rotational axis makes with its orbital plane. It is currently about 23.4 degrees and is declining. This tilt varies from 22.1 degrees to 24.5 degrees. It makes one complete tilt and back every 41,000 years. This change in tilt is directly related to ice ages on Earth. The last maximum tilt occurred in 8700 BC, and the next minimum tilt will happen 11,800 AD. The inclination of Earth's orbit drifts up and down relative to the present orbit, with the cycle having a period of about 70,000 years. Relative to the orbits of other planets as well. By calculating the plane with unchanged total angular momentum of the solar system, we can define the orbital plane called the invariable plane. It is approximately the orbital plane of Jupiter. The inclination of the Earth's orbit has a 100,000-year cycle relative to the invariable plane. This 100,000-year cycle closely matches the 100,000-year pattern of the ice ages. A year on Earth is directly determined by all the various orbital motions of the Earth. So, if someone tells you how many years old they are, you might ask them, is that sidereal, tropical, or anomalous years?
Okay, I did bring my props with me, what I showed last time, but there's no time to really go through it again. But I'll be here in the break. If anybody has any questions at all or wants to see how angular momentum works again, I'll be more than happy to demonstrate that during the break again. So, hope you enjoyed it.
Okay, I think next meeting we'll come in with a calculator so we can all recalculate our ages. We'll pick whatever gives us the least number, the smallest number. Maybe you could just say how many times have you gone around, but then that wouldn't change either. I know, we've got one person who'd like to take the longest, I'm sure. Well, welcome to the January meeting. I think we're going to have a good crowd tonight. It's cold. January is always good for filling the room. How many of you are here for your first time? We do have you. Well, welcome to the group. One of 230 some of us now. We see it growing. My name is Jay Anderson, if you haven't already found that out, and I'm the president this year of the center. You can see from tonight's program, most of you, I hope, have seen the emails and seen your Winnicentrics, which tells you about these, but Mick has already done the beginner session for us, and Gail is going to be talking about her constellation of the month. I'm going to cover off what's new, what's happening in science of astronomy. Jennifer is elected for a break this month. Brian's going to cover off what's coming up into the sky in the next month that we might want to look at. And I think tonight is a conjunction of Saturn and must be Venus. Wouldn't be Jupiter unless any Nick's calculations are completely wrong if it was Jupiter. Leo is going to lead us into the land of spending more money. He's going to tell us about the construction of his observatory. Since I'm doing that myself right now, I can testify to the fact that we should be calling, we could replace all the S's with a dollar sign, but I think Leo will show you how dollar signs can be kept fairly small. We'll take our break. We have coffee at the break, and then after the break, Mark is going to be bringing us back to Star Trek and the Star Trek universe. Well, this galaxy is an old picture I took 7 years ago and finally reprocessed. Have to be a little farther south from Winnipeg in order to be able to see that one, but it's a good big one, bigger than the moon. You get a long enough exposure. Once again, Brian, are we going to be having a members observing night tomorrow?
I don't know, I think it's too cold.
Too cold? It isn't minus 30? Well, maybe it is.
Yeah, it's pretty close.
It is. Yeah, we'll cut off at minus 30. How many of the new members are going to quit tomorrow?
They will have
Let's just say if it's warmer than minus 20 or something like that, we'll go ahead with it. Will that work for you?
Yeah.
So the members observing night is held at our Glenley Observatory. If you don't know where that is, you can speak to me or Brian about it during the break. We have our Christmas party coming up. Many years ago we decided that Christmas was a really bad time to have a center Christmas party because we all had parties. So our Christmas party is held sometime in January, and this year it'll be January the 23rd, and it's going to be at Gail Wise's house, which is 81 Triton Bay. Memory serves me correctly. We will send out email notices about that ahead of time, and it's also will be on the web. We don't publish the address online. There's a link there to phone me if you want to know where it is. And it's a potluck, and it's for members and family. So bring food, bring drink, bring your significant partners and family, and come and enjoy yourself. Mick has promised us to talk about the mysteries of Mars. He hasn't specified very much about it for next month, so I'll be talking to him to find out just what he's got in mind, but so far that's what we're looking at for the February meeting. There are some magazines here that have been picked over quite well, but there's some issues of the journal, Scientific American and Sky News, for those of you who'd like to go home. There's a few of them. Looks like the surplus Sky and the Fluscopes have already gone. Haven't said anything about the telescope loan. This is a slide I show every month, but we do have telescopes to loan out. If you want to borrow one, you can see Stan Runge here in the middle. And Stan is the supervisor in charge of telescopes. And the way it works is you borrow it for a month, and if nobody else has asked for it in the intervening time, then you can keep it for a longer time period. But you are expected to pick it up here and bring it back here so that they can be passed on to other people. And they come with enough instructions to be able to get you started. But if you're looking at the moon and some of those bright things in the sky, you just go around to the 5 brightest things in the sky at any time. You're bound to hit at least 2 planets this time of year. We also, at the observatory, have an 11-inch telescope which you can use. Brian will give you some instruction on it if you want to use it. 12-inch? Oh, of course, the universe is expanding, isn't it? There's another processional effect that Mick forgot to mention. No, that's right. I own an 11-inch. Okay, so that Glenley is 15 kilometers south of the perimeter.
You mean 16?
This is in current kilometer units. Tonight we'll have pizza, Boston pizza. I forgot to tell them we were coming. I hope they remember us. Anybody else got anything they want to pass around? Anything to say? No? Okay. Well, let's bring up Gail, who will be our first presenter tonight.
Is there a religious contract? Not that religious. Is this the DC contract? Absolutely don't know. Canis Major, the big dog, is visible in the northern hemisphere from November to March. Here, the galactic plane is crossing our field of view, so this constellation is just full of deep sky objects, especially open clusters. When you go outside right after sunset, take a look to the southeast, and you'll see a very bright white star. It's very easy to find because it's brighter than anything else around it. The official name of this star is Sirius, but it has the nickname the Dog Star. Sirius is the brightest star in the night sky. Its magnitude is minus 1.44, and it dominates the constellation Canis Major. It marks the dog's nose. Sirius, the star, was seen as the dog civilization. The Persians, the Babylonians, and the Arabians. Even in faraway China, this star was seen as a heavenly wolf. The Australian Aborigines saw it as an eagle. The Greeks don't seem to have seen a constellation here, but they were only concerned with the bright star Sirius. Not until some time later did the Romans associate other nearby stars with this star and Procyon, and determine that the two were dog figures. Arabian astronomers went along with this notion, and they called the two constellations Canis Major, the greater dog, and Canis Minor, the lesser dog. It was once believed that the intense heat of summer drove dogs mad. And in Greek times, Sirius rising just before dawn, before the sun, marked the start of the hottest part of the summer, the time that we've come to call the dog days. As a winter star, Sirius is often blamed for uncomfortable extremes of cold. We say that Sirius is in opposition at this time, as the sun has just set and the two bodies are on opposite parts of the sky. Sirius is interesting in another way. It's a double star, which means that it has a tiny companion that spins around to keep the dog company. It has a 41-year orbit. This companion is a white dwarf with a density 125,000 times the density of water. 1 cubic inch of this star material would weigh 2¼ tons. And what is the name of this tiny companion to the dog star? It's called the Puck, of course. The belt stars in Orion point down to Sirius, and Canis Major and Canis Minor are Orion's hunting dogs. The big dog is shown in the sky, assisting Orion as he's out hunting. That was Orion's favorite sport. Following on Orion's heels, his eye fixed on Lepus the hare, he crouches just below Orion, ready to pounce. The two dogs, Canis Major and Canis Minor, they have nothing to do with Boate's hounds, the Canis Venatici. The sky is just filled with dogs. The ancient Greeks said that the big dog was Lelaps. His name means hurricane, and he could run. He was known for his speed. He ran so fast that not even the fastest deer could outrun him. Many people owned this dog. His last owner was Procris, the wife of Cephalus. It was a gift to her from King Minos of Crete. Minos also gave her a magic spear, which always flew directly to its target and never missed. Alas, this spear was the end of Procris when her husband Cephalus accidentally killed her with it in the middle of a hunt. As a result of this tragedy, Cephalus was banished. He inherited Lelaps, and eventually he ended up in the city of Thebes, which was being ravaged at the time by a vicious fox that was ravaging the countryside. This fox was a very special animal that could run so fast that it could never be caught. Cephalus set the dog Lelaps on the trail of the fox. Off they went, almost faster than the eye could follow. The dog that could catch any prey running after the fox that could never be caught. At one moment, the dog would seem to have the fox within grasp, but would only close its jaws on thin air as the fox raced ahead of it again. The two speedy animals were caught in a race that could never end until Zeus intervened and placed them among the stars. The dog became Canis Major, and the fox is now Vulpecula. Still out of reach of the dog, he's way over on the other side of the sky. About 4 degrees south of Sirius is M41. It's a really nice open cluster. It measures 38 minutes across, and it can be seen as a hazy patch to the naked eye, and it's easily visible with binoculars. A telescope will show a wonderful little cluster of about 100 stars. Its total magnitude is 4.5, and its brightest stars are 6.9. This really is a nice open cluster. It measures more than half a degree across, bigger than the area of the full moon. To find M41, follow the backbone of the dog down. We'll find a little triangle of stars right about there, and it's just right beside it. And it's got a 6 magnitude star in the field, so you can easily see it. Now, if you're not driven inside by the cold by now, spend a little time sweeping through Canis Major. It has a lot more nice open clusters embedded in the Milky Way. NGC 2354 is a medium-sized cluster. It's at the southern end of Canis Major. It has a diameter of 20 arc-minutes and a magnitude of 6.5. And you can find it very easily by using this triangle that forms the dog's hind leg as a guide. Just 1 degree east-northeast of 2354 is NGC 2362. It's only 8 arc-minutes across, so it's a little bit difficult to find with binoculars. At first it looks like a patch of nebulosity, but even a small telescope will resolve it into a rich little cluster of about 40 stars. They range in magnitude from 7.5 to 13. NGC 2362's total magnitude is 4.1. NGC 2360 is another nice little open cluster. Its magnitude is 4.1. This was one of Caroline Herschel's discoveries. It's very large, well, quite large. It's 13 arc-minutes across. It's quite condensed, very rich, with 80 stars from magnitudes 9 to 12. A fifth magnitude star is right to the west. I guess you can find it easily. This is a beautiful cluster. You've got to get out and look at that. I don't care how cold it is. It is. NBC 2359 is an emission nebula. It's known as Thor's helmet or the Duck Nebula. It's quite large for a nebula. It's 9 by 6 arc minutes. It's called the Duck Nebula supposedly because it sort of looks like Daffy Duck, with the duck's eye being the nebula's central star. There's his eye, there's his head, there's his feet. Can you see it? It's also sometimes called the Witch Head Nebula. Okay, the only obvious place I could find to put a cat in Canis Major was here with the witch. So with all these dogs around, I don't think she'd stick around very long anyway. Near the dog's left front paw, two spiral galaxies are passing each other like two ships in the night. The larger and more massive galaxy is NBC 2207, and the smaller one is IC 2163. Their magnitudes are 11.6 and 12.6. Strong tidal forces from 2207 have distorted the shape of 2163, flinging out stars and gas into long streamers 100,000 light years into space. 2163 is swinging past 2207 in a counterclockwise direction. It doesn't have enough energy to escape the gravitational pull, so it's destined to be pulled back and swing around it again and again. Trapped in their mutual orbit, these two galaxies will continue to distort and disrupt each other. Stick around for about 3 billion years and you'll be in for a spectacular show as the two merge into a single, more massive galaxy. The space between stars is so vast that when galaxies collide, the stars don't come anywhere near each other. A lot of large galaxies are assembled from a similar process of merging smaller galaxies. Because Sirius and Procyon are on opposite sides of the Milky Way, we need a myth describing how these two companions became separated by the Great Sky River. The Arabs have a story for us. It's about two sisters who tried to follow their brother across the sky. They came to the Great Sky River. They plunged in to swim across. The older, strong sister managed to, and today we can see her as Sirius on the southern bank of the Milky Way. But the younger sister was too weak, and so she remained on the northern bank, where we still see her today as Procyon. Dogs are regarded as man's best friend, and they're symbols of loyalty, watchfulness, and protection. And as long as the stars still shine, Canis Major will still be up there, and we will never be alone in the dark. Thank you.
Sirius to me always means it's winter. Look out there, 9 o'clock in the evening, and that bright star that's hanging in the south, and you know it's got to be cold out there. It's a blue star, so it looks cold feeling-wise. Okay, let's see what's going on in science right now. There's no end of things when you start putting together this little talk. We have an abundance of things to talk about, but everything in science news these days seems to involve dark energy, black holes, and unseen mass. And how can you talk about astronomy if everything you talk about is invisible? So we have to select carefully the things we can see. One of the things that's been done at the University of Wyoming is going back and looking through images from the Schweitzer and WISE satellites, because they're both infrared satellites, and what they were looking for was to see what kind of structures were around fast-moving stars. And these are stars that aren't sort of in a gentle orbit in our Milky Way, but seem to be speeding along at some unusual velocity. They found 200 different stars that they wanted to look at. Each one of these had what they call shock waves or bow waves ahead of the star. They're associated with them. And there were 200 candidates, so they took a look at about 80 of them to find out what their specific characteristics were. And they find that they're all, or almost all, young stars. They're massive, so it means they're very, very bright, although many of them have around them. If they didn't have those duck envelopes, would be among the brightest stars one they really focused in is Zeta Ophiuchi, which you can see here in this rather lovely picture in infrared light. Now Zeta is the bright blue star in the center, and it is moving very, very quickly from the lower right to the upper left in this image. And being a hot young star, it actually has a very, very strong wind that blows outward from the star. And that wind compresses the gas out in front of it, which is then, because of that compression, excited to the extent that the electrons in it are elevated to a higher orbit, and when they settle back, they give off infrared light. And you'll notice out in here, this greenish tones well away from the star are relatively quiet. Sort of represents the unexcited part of the Milky Way, and then you come in closer toward Zeta Ophiuchi, you get the greens becoming brighter and brighter. This represents, in the most part, the ultraviolet light that's coming off of that star, and which is exciting that gas to make it fluoresce. But this one is dust rather than gas, which is out here, and the dust is being compressed, and it's that compression and the shock wave that's created. So it's very much like the bow wave on a boat, except that it's running out ahead of the actual star itself because of the intense wind of solar particles that's coming out forward from that star. I should point out that that entire envelope of emission is totally invisible. In visible light, you couldn't photograph it with your own telescope, even though it's a pretty sizable object, simply because all of the emission is in the infrared, because it's dust that's giving off the emission, not a gas. This is a Chandra image, another satellite, showing a sort of similar feature. In this case, we have a large galaxy cluster in through here, and it's got this one single galaxy that's plowing through the cluster. You can see many, many members of the cluster here. And then it plows through this cluster. The cluster itself of galaxies has gas in the intervening space between the galaxies. As this galaxy moves through it, all its own dust and gas stripped out behind. And it's kind of a process that when you think about it, it seems logical that it would happen, but of course now you're dealing with scales of tens and hundreds of millions of light years and watching the same process going on. And it actually seems that this galaxy is doing pretty much the same kind of thing. The length of this would be twice the size of the Milky Way, and so we can see in the huge scale, the extragalactic scale, some of the same sorts of processes that are happening with Zeta Ophiuchi. In this case, this is glowing because it is a little bit of a shock wave out in front of it. In here, these are not stars or galaxies, but just a bright part of that gas. And so what we find is that all of this gas that's been stripped out of this galaxy has done two things. First of all, this galaxy has stopped its star-making processes, because there's not enough gas left in it to form new stars. And secondly, this part in here has got not only a lot of gas, but that gas is rich in heavy elements. And we know, if you've been in meetings long enough, that the heavy elements in the universe came from the inside of stars, from the formation of heavy stars and their eventual explosion that blew their contents, their guts, back out into the interstellar medium to create the heavier elements. And so this piece of gas is very rich in atoms that are heavier than helium. It's another way we enrich the interstellar medium to provide dust and gas later on for the formation of new stars with different characteristics. This is a lovely image from Hubble of one of the molecular clouds in the constellation of Orion, in Orion's nebula. And what we're seeing here is behind this clump of dust and gas is a very, very young star. And that young star is sending out two jets of high velocity atoms and molecules that are then colliding with the gas around it and causing it to fluoresce. And These two stars are also very young stars that have just appeared out from their dust cocoon right here. So this is a process that's extremely common in any galaxy, and particularly in our own. And these excited regions caused by these outflow of jets are called Herbig-Haro objects. We also get cavities in it, and this structure in here is another cavity that's carved out by the jet of some other star that's behind this stuff that you can't see. So what we're seeing is that there's a great churning of the interstellar medium once new stars start to form. And these are stars that have not settled down into their steady existence, but are still collecting dust and gas as they collapse into their eventual stellar shape. And so these jets are created, most of these stars have a ring of dust and gas in them as it's inflowing toward the star that tends to take up orbit around the star, collects in a collar or donut of dust and gas that surrounds the star at its equator. And through mechanisms that are not entirely understood, as this dust then eventually flows down onto the main star, the star rejects a certain percentage of that material as a jet, almost a relativistic jet, with the material moving out of it at a significant fraction of the speed of light. And so these Herbig-Haro objects are things you can find and photograph and look at quite commonly all across the sky that we have available to us, particularly in Orion, although they do tend to be relatively small objects. The James Webb Telescope, after all these years of talking about it, is finally coming together. And here we see that the first dozen of the 18 mirrors that are going to be installed in it are now in place. They'll put the final 6 on in the next 6 months. This doesn't mean that the telescope is ready for launch. That's still 3 or 2 years away, 2.5 years away. But it does mean that once these are in position, they can then be taken into the vacuum chambers where they're tested and calibrated, and presumably they won't make the same mistake with this one that they did with Hubble. And
18
eventually we'll get this in orbit. I've always said to myself that it's a pity that this is going to be an infrared telescope and not a visible light telescope, because we're going to lose all of those Orion-type pictures. But when you start seeing some of the images coming out of current infrared telescopes and microwave telescopes, I don't think it's something we're going to have to be concerned about. This telescope, of course, will be so far out in orbit that there'll be no astronauts visiting it to do anything. Once it's out there to stay, because it's going to be about a third of the weight of the sun. The Curiosity rover is kind of having a good time these days. In spite of a wheel that's not working as well as it could, it's chugging along steadily. And what it's done now is it's reached this area of black sand dunes that are at the foothills of the mountain range that is its eventual target. And so here we have a panorama view showing the dunes up close that lie in this area, and here when they're right up against it. These are dunes that are up to 50, 60 meters high, so they're pretty substantial dunes. And some of the other pictures that you can look at show sort of the thing you'd see if you went out to the star party that we hold in September and had a look and hike in the dunes there. This is actually a close-up of what the particles look like on one of these dune faces. They're actually quite coarse material because for the most part the lightest material is removed by the wind. Now you have to realize that these dunes are sculpted on Mars in an atmosphere that's probably close to 500 or 1,000th of the density of our own atmosphere. So it takes a wind of 300 or 200 kilometers an hour to actually start moving that stuff around. And Mars has that kind of wind at the right season. This is the first time that Curiosity rover or any of the rovers on Mars has actually gone to take a look at a dune. And this one is particularly interesting because its composition, being black and not like most of the other dunes, which are more of a reddish sandy color. We're still getting high-resolution images down from Pluto, and this one, the most recent that they put out, is a part of that big white plane that was visible in the planet-wide pictures, and what they call Sputnik Planum. And this is primarily a surface of frozen nitrogen that seems to have welled up from below, still as a solid, not as a liquid, and as it got to the surface, it formed these large blocks like this. And this is a very familiar pattern to us because our own Arctic tundra has patterns like that from they're more like convective cells that have come up from underneath and reach the surface where they then evaporate into the atmosphere or are scoured away by the winds of Pluto. And you see these little black lumps here and there, which are thought to be dirty icebergs that are sitting on the surface made out of water ice. We have a little X in here. That was the subject of this picture. X marks a spot. So what it does is it marks this old spot where four of these convective cells once came together, but is now gradually fading away. ALMA, the Atacama telescope, the radio telescope array, has been taking some spectacular pictures, even though it's a radio telescope, its resolution is so high. And this is actually pictures of a star and the dust shell around it that has this mysterious donut hole in the middle of it. So we have an artist drawing of what it represents. And what it seems to be is a fairly young star in here that's still forming, still carrying that dust donut around it that I just discussed. And there's a small planet which is going around this star, which is cleaning out and collecting the dust in its immediate vicinity. So when they see these donuts in the microwave signal, they immediately theorize that these dust gaps are being caused by a planet. Sometimes you'll see these with a ring that's been cleared out. In this case, it's the hole of the center. This scale of this image is about equal to the cross or the size of the orbit of Neptune here in the Earth. Inside this hole, this is all dust, but inside the hole they found quite a bit of gas. So what's happening is that the planet is scavenging the dust, but the gas is staying behind. And this gas, when you examine it in very fine detail, has a smaller hole that is sort of more zeroed in on the planet. So this was taken when the ALMA telescope array was only about 1/3 of its current size. The ocean is only 1/10 of what the and it's nearing completion now. So you can imagine what you might be able to see in these with 10 times the resolution you have here. This is a nice little picture of one of the NGC galaxies, an unusual one. It's difficult to interpret until you have a look at this image, which is I believe it's an ultraviolet image of the whole thing. So this galaxy is this bright one here, and this galaxy here is this one. And what you see is this long arc of material that once you're aware of it, you can sort of see this arc stretching out through here, inverted from the other image. But that is actually a result of some galaxy in the past that's made a high-speed pass through this one and kicked out this long tail on both sides of dust and gas that is stripped out of the main galaxy. It's not associated with this galaxy, which is called the Seashell Galaxy. That seems to be in foreground object, but it looks one of the strangest galaxies in its own right. Anyway, it turns out this galaxy has the appearance of a dwarf galaxy, except that dwarf galaxies normally have very old stars in it, and this one is very active and full of very young stars, as are many of these other clumps out in here that came from that collision. And so what we're seeing is kind of the formation of small galaxies associated with a larger one, but these are galaxies with completely different characteristics because they're so young and are so active in star formation. So there's a little sampling of the things that are happening over the over the world of astronomy news in the last month or so. And I do believe we have Brian up. January. All right, so we talked about a little bit about the planets. Of course, Mercury is well placed in the evening. We have Venus, it's going to shine brightly in the morning, and Jay has mentioned earlier that conjunction of Saturn on January the 9th. Mars will be start to show up beginning of January. It rises around 2 a.m. in the morning, Virgo, and moves Libya on the 17th. Next we have Jupiter, that rises in the east in the late evenings and gets its retrograde motion in the 8th. Of course, Saturn is in the dawn in the morning, which I'll show you exactly. I decided to show you this, and I thought it would be kind of interesting to show you exactly in relation to Earth. Of course, that's Earth, and we have Jupiter, Mars, and Saturn, and I'll show you the next slide how they appear in the sky. And there's Venus partly in the morning there. One interesting thing that I like about it is Mars. Mars will move in. This is, of course, someone was talked about the zodiac signs there. Okay, so Mars, basically, it's going to move. This is Earth, this is Mars, and we're going to catch up to Mars roughly about here, which is about June, sorry. We'll move on to the next slide. Oh, sorry, I'm going to go back here. Sorry, what I forgot to mention is the rotation is this way, it'll be counterclockwise. Okay, now for the next slide. Okay, we have, now that's supposed to be Saturn and Venus. They're about a half degree apart on January the 9th, 7:15, about an hour before sunrise. Then we have Mars, and then we have Jupiter up there. Next slide here. This is supposed to be Mars. As I mentioned earlier, it's going to start to rise around 2 o'clock in the morning. I said for 2:16 because you can see Mars is right there. We have Jupiter, and then that's about it. So actually, I'm going to go back and slide there. So as I mentioned before, we got Saturn, Mars, and Jupiter. I'll go back and slide again. And you see the relationship with Jupiter, Mars, and Saturn, and Venus. You can see how they all line up. Now for celestial calendars, there's not much happening for January, other than we had that meteorite shower on January the 4th. But for me, I did watch some of it. I was at Glen Lee, shoveling snow there. And thank you some of you guys for joining me to clean it, because our equipment started to freeze up. Okay, of course, January the 10th, we have the new moon. January the 24th, we have the full moon, which is not good for us. And of course, this month we have Comet Catalina. Now here's some of the highlights for Comet Catalina. Of course, it's half a degree off the Earth, beginning January the 1st. Now, according to my information, they said January the 12th was closest to Earth, which is roughly 66.9 million miles away, which is roughly 0.72 AUs, I believe. And of course, it's going to happen next week. What's been interesting about next week is you'll be able to detect within 30 minutes, be able to detect some sort of motion within it. Apparently it's going to move about 5 arcs in an hour or 2 degrees per day, which is pretty fast for that whole next week, starting January the 12th, at the closest point. Of course, on January the 14th, Comet will pass through its major. January the 14th, it passes through or starts getting the handle, Big Dipper. Of course, January the 16th. At 17th, it's going to be, 68 million miles
the next point there, and it passes through that bend in the Big Dipper's hand. Now that star, Mazar, apparently is supposed to be a 5th magnitude star, so that's a good reference to see how bright it is in comparison to the comet. And of course, then it was actually very cool in the other constellation. I think it was 1 or 2 points. No, it's 40. Okay, now I showed this last time. Of course, this comet is supposed to have 2 tails. One's the ion trail, and one's the dust trail. It tends to bend towards the other motion of the comet. Now, thanks to Sheila, I got permission to use this. So this is her picture of Comet Catalina. And if I'm right, I believe that should be the ion trail, see, and then there's a little bit of dust trail there. Is that right? Yeah. That's the way I see it. I think it's that Arcturus? Yep. Okay. All right. That's the next shot. All right. Moving on. Okay, so here's the projected path of the comet. I'm going to scoot it a little bit. So, as I mentioned before, January the 12th, that's where it's going to be the closest point to Earth. And then the 17th there, which is the band of Mazar, that star, the second star, is supposed to have a magnitude of 5, apparently. And then it just goes on and on. Now, my next slide, I really like this shot here. There we go. This is the path of the comet. So January 12th, that's the closest point. There's Earth, and that's your closest point to it. So it's just roughly 66.9 million miles. Oh, and the comet tail apparently is supposed to be like 500,000 miles long. That's pretty long. Oh, and the speed of it apparently is supposed to be 103,000 miles an hour, which is pretty fast for a comet. Now back here, I pointed out we have Comet Catalina right there. And I think it's the time, yeah, 1 o'clock in the morning on the 12th. So when it reaches the closest point to Earth, that's where it's going to be at. And I have the Big Dipper here, so the handle clamp points directly towards it. Now this latitude right here should be about 30 degrees. I'll give you an idea at 1 o'clock in the morning where it's going to be. Okay, my next slide here. Okay, this is the current prediction for the magnitude for Comet Catalina. So the whole month is right. Okay, so here's January the 12th. We have, well, they said what, 5.6 or something like that, but I think the current magnitude is supposed to be 6, I believe. Around 6 magnitude. And it's pretty much, it dips a little bit more as it moves away from the Earth. And the next slide here, I have the projected magnitude for the next several months up to September. So of course, this is January. And you can see starting February is going to dip quite, the magnitude is going to dip quite high, I guess, when it starts moving away from Earth. So just kind of bear in mind, we start taking photography or looking at it, and it's going to drop quite fast. I think that's all I have for it. And that's the projected. And that's it.
Well, when you get into this kind of temperature, there's nothing like having your own observatory in the backyard. Mostly because there's always somebody in the house who's making a pot of tea for you, in my experience. Although that only goes up to about 11 o'clock at night. Later than that, you're going to make your own tea. So Leo's going to tell us about his observatory and his little construction project. It's refreshing to know that over the past 5 or 6 years, quite a few small observatories have been appearing in backyards. So here we have another one to add to the whole.
Thanks, Jay. Can you hear me in the back? Yeah, okay. I'm looking for them. I don't have my glasses on. Okay. Okay. So, before you start any building project, you have to figure out what do you want to do with it. One of the things I learned early on in astronomy and coming to meetings was the easier it is to use new instruments, the more you use them. So that's one of the purposes of having an observatory. The other one, for me, this was the second one I built, was I wanted something a little more practical. So I talked a lot to Stan about his dome that he has, and that's why I came up with those two aims. One is as small as possible, and the other one was, if I move, I want to be able to take it with me. So that's what it looks like. You've got rails here, and the roof just rolls right off, and you can just push by. And this one's a little bit different because the sides I can pull down. When it's small, your scope is closer to the wall. So the wall is a greater obstruction. Hence why this hinge. So this is just an overview of what went into it. Tin roof is for weight, so you can push it. You put shingles on, a bundle of shingles is 7 pounds. The 3 sheets of tin on that are less than 50. So that just gives you a weight comparison. One of the things I learned from my last one was, when you want to get at things, if everything is screwed down, you're not getting at anything unless you want to cut it. So that's why that is. And the last thing here, I'll show you a picture of these cutouts in the floor. I used the tripod for the mat. I didn't put a pier in it. Again, a little less effort. I got the tripod anyway. So something different to try. So that's what the scope looks like when it's all closed up. And there's just under 8 inches between the beam there and the finder scope. So when I said small, I meant small. The ceiling here is from that 2x4 there to the floor, 66 inches. So if you're taller than me, you have to bend down. Because I'm 68 tall. What else am I going to say? Okay. A couple things you want to see on the inside. The lower part of the walls are painted. That was to reduce any glare, so it keeps your night vision. The upper parts aren't because they fall down. And you can see this is a Newtonian, and so the tube is actually 44 inches long. So the clearances get really interesting between the walls if you start moving this thing around. And in fact, you cannot rotate it vertically because you will hit the roof. So that's just some of the little things you got to watch when you're playing in there. 2 people is a crowd in there. So that's what it looks like with the side, the south. This is the south wall put down. It's an LED rope light, kind of used for Christmas. So when you want to do things in there, you don't want to lose your night vision, you just plug that in. And that's a power bar. That's actually one made for you can't just use a regular bar because of moisture. The other beauty of this thing is it also has a nice switch on it right there, and it's waterproof. Okay, the corners are 4x4 posts, and then the walls are into the posts. So it made construction a little harder because you had posts and then the framing between them. But when you go to move this thing, you just have to unscrew the lower parts of the walls with a screwdriver, preferably a broom. and away you go. So it will come down in 4 pieces, and then the roof, and then the floor. So, talked about the floor. And so those are the cutouts I made for the tripod. And this is the access panel here. So I deliberately made it that way. So if I ever want to get in underneath at something, this here is where the main power comes in. And then that is a heater cord, or a block heater. It runs underneath this leg, and you just unclip it, and then the cord stretches across there. Boards that you put in the hole so you don't fall in the dark and break your ankle. And that way you're not tripping over anything. So there's nothing in the foot. So that's with 2 of the sides down. So that's the west side, that's the south side. This is probably a little bit lower than I needed to go. But once you start cutting, you're committed, so get going. So this is actually 28 inches and a half that comes down. So basically, the scope can be perfectly horizontal, and the bottom, remember it's a 10-inch scope, it's that big, bottom will clear right here. So you could theoretically look at something exactly on the horizon, not that you're going to. This is the west side, comes down, this one here is 18 inches. And the east side is a little bit less at 15 and a half. Reason being is things rise in the east. But I didn't want to lose 15 degrees because that's what that represented from where you would look at in the sky. Especially around March if you want to do anything with Messier, then your walls are in the way. So that's why I even did that on the east wall. Other things I want to point out, the material here is a pre-finished panel called a smart panel. And it's a turn-in roof system, so they come together like that. You don't even know the strips to see. Easy to work with, but not really liked. They were probably like the heaviest item I had, 4x8. The roof is held on with a system of bolts and turnbuckles, and you can see a turnbuckle here and just a little bit of it there. And at the front, a bolt here and a bolt there. Okay, so the electrical, this is something I've never done before, but again, talking to Stan about his setup, and I was thinking about how many times I've tripped over an extension cord in the dark. So I decided to do something a little bit different on this one. So I built in an external connection, and I put it on that one post for the rail, and then I used it out with an outdoor power bar, and then the red LED lights, and I also have, you can see in the picture there, a white 40-watt bulb, and then the 11th floor. So a little bit hard to see. I didn't want to have a lot of slides because I was told I didn't have much time. This is the power here to the post. And so I have an extension cord that runs from the back of the house about there, out and across, and you plug it in. And this is made up of just 2 pieces of pipe that you would normally use for a SIP. Okay? So one's a coupling, and the other one is the screw it down. Put them together, drill a hole, and the wire is through the cap, and then put silicone around it. So your extension cord plugs into the bottom. It's only external plug. I could have bought one, but I thought this thing will be out there. It's a bottom. Weather. And that's cheap. I think that was $3.99 for the 2 pieces. There's a close-up of the power bar, and then this is the main power coming up, the power bar, and then this is the power extension cord that goes under the floor, the scope. And you can see the panel here is in place, and so this is where you're walking. The doorway is 25 inches across and 63 high. That's because the walls are only 66 high. So I didn't have a lot of margin there. So you got to ductility. It reminds me of being on the ship or something. That's just a tripod view. So you can see the floor, you can see the inserts, and you can see where the flow comes in. So again, it comes out right here. It doesn't actually touch the tripod, and the tripods are cut out, so nothing actually touches glass. So if you wanted to do photography, you don't have to worry about the jitter, because that's the last thing we want. Even when you're observing with a 10-inch, any kind of motion makes everything just switch. I don't want to bore you, but there is a quick list of some of the technical things. Inside, the width, so north to south, 72. The length, 9 inches. And if I did anything different, I would probably made it about 6 inches wider. Because when you're walking around in the south part, and the scopes there, the walls right here, I forgot that you wear winter clothes in the winter time, and you catch us now on the scope. So another 6 inches would be good. One of the reasons I went to those dimensions, though, was to keep everything stocked. So the roof panels were one size, 2x4 there. So that's why I had those inside dimensions that way. There's the fold down, the wall, the roof. The tin roof is actually really easy to work with, because they're rippled, so you just join them and the screws in this case. Clearances, yeah. There's only 19 inches from the bottom of the leg in the south wall. So that's always fine. There's not a lot of room there. There's enough to sit, because I have a little stool to sit on. And I can actually lean my arm around and look into the south wall. Wheels, on each side, they're 2-inch, and they're just, I guesstimate the roof to weigh around 800 to 1,000 pounds. And those wheels are rated at 90 pounds each, so that's over 1,000. And just some of the other stuff. If you want more detail, I can give you. I didn't think I would bore everybody. Question? Yes.
How much did you spend on that project?
If I count everything, including the paint, it'll be about $850.
How many hours?
Oh, well, yeah, that's a really good question. Lots, because the first one I built was just straight walls and a roll-off roof, and what I did is I angled the roof so one wall was higher than the other, when I rolled off. Whereas this one, hard to see, but the roof is actually tilted, but not a lot. Because one of the things I realized when I built the first one was that you don't need a lot of tilt, because you take the snow off because you're going to observe it. And now, if you're going to go away from the winter, you would build it flat. Yes?
Yeah, you mentioned building it that way because of potential portability.
Yes.
How about floors? Like one unit, we have 3 building containers?
No, the floor is one unit, and hard to see. There's one picture I could probably come back to. Yeah, there it is. It sits on, these are called patio blocks. They're foot square. And so the 4x4 post there is just sitting there. You take the walls off, 2 people can move the floor.
It's like 6 by 8.
Yeah. Okay, maybe 4 guys. But again, you can put that on a trailer and move it in sections. It's not like a dome, plastic domes, which are quite light. But then it's way cheaper than plastic dome. Am I taking too long? One more?
Any other?
Anybody else?
What's your tripod sitting on? Like, is it right on the ground?
No. Yeah, I guess that one sure might show here. There. Okay. If you look carefully, there's a little block 2x4 block there. And what I did is I drilled out a center hole in it, so that because of the bottom of the tripod's leg is actually a little rounded, so it sits exactly in there. And then I took, these are carriage bolts here, drilled 2 holes, and there's, I can't remember how long they are, 4 or 6 inch into the dirt, so the blocks don't move. So I can take the tripod out, put it back at a pretty close polar line, just like that. So if somebody asked me how long, well, it's the kind of detail I actually sat bottom on it. How am I going to do this? How am I going to do that? You know, the shapes, the sizes of these cutouts all varied on the angle and the fact that the ground's not level. So they're not the same shape. These 3 are all different shapes. Makes it a little bit harder. I guess I should have leveled it. Yeah, he said I'd take it too long.
Well, let's leave any other questions to coffee and cookie time. We'll take a break now and come down and enjoy.
Incredibly bipolar.
Yeah, I can see white. I always sometimes I do. Well, 40K, I guess it's one goal.
All right. Well, thanks everybody for coming. Anyway, here's my presentation for today. Something I've been thinking about for a long time. You know, astronomy and Star Trek have been part of my life for a very long time, since I was probably 12 years old. So I wanted to do, you know, kind of a link between everything that you see in the show. So it's about who played with my presentation? Hang on. Okay. So yeah, sometimes when I look up at the sky, I'm wondering, where's Vulcan, where's Kronos, Homeworld, where's Rigel? Well, we know where Rigel is. You know, that's what's special about it. All these different planets that I hear about on Star Trek, and I was looking in the sky and I'm like, hey, where are they? And can we actually do a presentation on this? Well, sure, why not? So we're going to start on Earth, head on to the solar system. And when I talk about objects in the solar system, I'm going to go pretty good there. A pretty good speech, because Brian did a pretty good show for us today with his What's Up segment. And we're going to head out to our galaxy and get started. Well, this is not an astronomical object. It's just a star. Riverside, Iowa. It's a place I visited about 7 years ago. And it's a future birthplace of Captain Kirk. There I am standing where he's, I guess, going to be born. And while I was there, there were 3 Star Trek actors, Walter Koenig, Turkson Kate, and Michelle Nichols. I got my picture taken with them. No, it's not Photoshop. I actually met them. So, the Earth and the Moon in Star Trek, well, you know, the Enterprise goes to different worlds. It's really interesting to see that. But sometimes it's nice to see when it comes back home, just to see what the Earth looks like in the 24th century. Well, it's a planet, you know, they eliminated poverty, greed, and pollution. And in the 24th century, the Moon is inhabited by 50 million people. So, be a nice place to see. The Earth, well, it's an astronomical object, but, you know, you're never going to see it in the sky. You can try, but you got to go to the International Space Station to see it. So this is a snapshot I got last year. Yeah.
You can see my house.
Yeah. Right about there. There's Winnipeg right there. Well, this was fantastic. I saw this on the streaming video. And I'm like, wow, you look at that, you can see the lakes. It was a real clear, cold day. So I took a screenshot. I said, this is great. It's the best view I've had of our province from space. The moon. There's a lot of things to see on the moon, but I'm just going to go quickly through it. This is a really nice picture taken by the Chinese spacecraft over here. Oops, pardon me. I gotta get used to this. Right here from they call this the dark side of the moon, but no, it's the far side of the moon. And I do like the lunar libration caused by I guess it's how oval the moon's orbit is. Sometimes the rotation kind of goes ahead when its revolution around the Earth, and sometimes goes behind, so it kind of gives it a wobbling effect. So rather than going through the whole moon surface, I just had to talk quickly about solar eclipses. I guess we're going to have a few talks about that coming up, since we're going to have a solar eclipse coming next year. Well, is it about a year and a half already? Total, depending on the moon's orbit, it's tilted about 5 degrees. Either it goes, the shadow goes above the pole or below the south pole. So we don't have an eclipse, but sometimes it does happen when the umbrella will touch the Earth's surface, we're going to have an eclipse. This one I got about a year and a half ago at the Assiniboine Park. We had a RASC gathering for the public to show the eclipse. So I got this picture with my phone. I don't have any fancy photo equipment. I usually just take pictures with my phone. So I got this one through a telescope eyepiece. You can see there's quite a massive sunspot over here, which the moon is covering up. It's really nice to see. So this one I got when I go back here for a second. When the umbra doesn't touch Earth, when the moon is at apogee, the umbra doesn't touch Earth, this is what you get. You get an annular eclipse. I got this at Snyder, Texas. That's just west of Dallas, close to Abilene. I took a big risk. I couldn't miss this eclipse into the clouds. And you could see all these clouds that were just in my way. I was driving up and down these country roads, and I saw this beautiful canola field lit up by the sun, and I was like, oh, God, should I? No, I can't do that. So no, I didn't go there. I was driving all over the place, and I finally got my shot. But I wasn't quite centered to get, this has a perfect annular eclipse from the sun at sunset. But close enough, you know. If I went a little farther west to get it centered, I would have been in the trees, so this one got shot. Total eclipse, well, I don't have a picture of it yet because I've never seen one. Am I the only one who hasn't seen a total eclipse yet? Who hasn't seen one? No? Okay, good. Thank you. I'm not the only one. So this is the path it's going to take next year. Maximum eclipse is going to be right here, but I don't know, weather conditions probably may have to go on this side of the United States. But more to come, I guess, in the coming months about this eclipse. Now we had 4 total lunar eclipses recently. And I saw, I think, about 3 out of 4. This is the third one because of cloud cover. So I got this one. This, I think, is the first one, the first tetrad. Next eclipse for 2018. You know, we've had 4 in a row. We can wait a couple of years for another one. The best one I saw, I think, was the very last one we had September. I was in Falcon Lake with my parents. Clear skies, beautiful weather. We had a campfire. I had my telescope and binoculars to the side. We couldn't ask anything better. Okay, let's move away from Earth and the moon. We head towards the sun. And in Star Trek, the sun is mentioned a few times, only for time travel. I don't know, Captain Kirk had something with time travel. Did it twice, I think, in the original series. The most famous one was Star Trek 4, when he went back in time. He had a couple of humpback whales bringing back to the future. So the sun, that's another thing I could talk a lot about. I'm going to go quickly through it. These are a couple of pictures I took. This one here was last year. Beautiful sundogs. I missed the upper part here, but no, this is just a really, really nice picture. Had this one in Grand Beach probably 10 years ago. I saw these 2 pelicans coming by. I'm like, oh, I'm going to get them as soon as they fly in. The sun follows a 11-year cycle of sunspots and solar activity. And when you get the solar maximum, this is probably something that you're going to get. This was last March. This is the best oval I've ever seen for solar activity. So KP index was like about 8. I've never seen it so high. And there was a really beautiful beautiful aurora. Anybody see it that evening? Do you remember this? Nice pictures? Yeah. Mars, okay. So we do talk about it a little bit in Star Trek. Mars is where the Enterprise D and Voyager were built. And one of my very favorite episodes of Voyager was a flashback episode. This is a screenshot here. It's from one of the first Mars missions. I don't know if it was the first one. Ares 4, this just was the fourth one. First or second one. People were stranded on the planet because this spacecraft was sucked out by one of Star Trek's famous anomalies and Martian from a few years ago. So this is Mars from the closest approach to the last August 2003 of the Space Telescope. Mars is not as big as a full moon. I had to throw that in. And so yeah, this is all the technical details about Mars. One thing that was discovered in November 2015, the baby spacecraft that's in orbit determined that the Martian atmosphere is being eroded by solar wind. Probably because Mars doesn't have a magnetic field, it has a very weak one, so it's not very well protected from solar wind. This I enjoyed looking at is all the Mars missions so far. There's about 55 attempts, 26 have been a success. So going to Mars is very difficult. So these are successful missions, except the two last ones here, InSight and ExoMars. InSight, unfortunately, has been pushed to 2018. There's a problem with the spectrometer, I think, where the container holding the spectrometer has a leak in it. It's supposed to have a perfect vacuum, it has a small leak, so we can't get to the time for launch in March. It's being pushed to 2018. ExoMars is being launched sometimes in March, mid-March. So far, so good. The spacecraft is at Vancouver Cosmodrome ready for launch. So this is where you're going to find Mars this year. Right now, it's in Virgo, entering Libra, magnitude 1.2, rises about 250, and it's fairly high in the sky at 722. It's heading into a low part of its orbit along the background stars. Its opposition is going to be in Scorpius. It's going to be a close opposition. One thing about Mars is that close oppositions are always around Scorpius or Sagittarius. They're always low in the sky. So if what you prefer is having close opposition, or you just wait for farther opposition when it's high in the sky, it's Mars or Gemini. The next two oppositions, between 2018 and 2020, they're going to be a bit closer than that this year. Now we head off to the asteroid belt. I'm not sure if this spacecraft is called the Phoenix. It's the first spacecraft to go to warp speed. It was protected by the Vulcans, and that's how it led to that first contact. So I don't know if they actually went to the asteroid belt. So I'm just guessing here. A lot of stuff about Star Trek is, just inference of information. It wasn't, made to follow astronomy perfectly, so I just make some guesses. So they make a quick flight. It probably went beyond the moon, maybe up to Mars, but I'm guessing maybe the asteroid belt. So this asteroid belt between Mars and Jupiter is a very low mass. It's lower than I thought. It's about 4% out of the moon. And it has about 200 asteroids, which are over 100 kilometers, and probably about 1 million asteroids, which are around 1 kilometer or more. And there's also a small gap in the asteroid belt. It's caused by the gravity of Jupiter, and they call this the Kirkwood gap. And when you look at the zodiacal light, you see all that dust, about 10% of it is from asteroids. and meteorites found on Earth. I'm surprised. Nothing was that high, 99.8%. Anybody, Ralph, can you confirm that much?
Sorry, what?
That meteorites found on Earth are 99% from asteroid belt?
From the asteroid belt, yes.
Yeah, okay. So an object that we can find in the sky at Vesta is the second largest asteroid and also the brightest. Currently in Cetus right here, this area. And it's been visited by the Dawn spacecraft in 2011 and 2012. It's quite a bright asteroid. It grew from magnitude 5.1 to 8.48. Right now it's about 7.2. Ceres is the biggest asteroid. It's the Capricornus right now. And yeah, I found this asteroid being, actually it's a dwarf planet. It probably formed towards the outside of the solar system just because of all the ammonia that's been found. Ammonia is usually stable in very cold temperatures. So it might have been migrated from beyond Neptune to its current location. And of course, we still have Dawn in orbit around it, so we're going to have more information about it in the coming months. Jupiter. Yeah, in Star Trek we see it a few times. The Enterprise leaving Earth, by Jupiter, we have a Jupiter station in orbit. Where this is a scene from the last movie where they had some kind of starbase created, they were building a new starship. But Jupiter, we don't have to say too much about it, we know where it is. You can see it more in the sky. I added these two pictures. You can actually see this one. Not too well. I caught this picture here with the three moons. What's interesting about it, this was at Cinnapoint Park for Astronomy Day. I caught this picture at sunset, so the sky was quite bright, and I found the three moons right here. You can't really see it, trust me, they're there. Who else was there that day? Do I have witnesses to confirm that I actually saw the moon? So this one here, this is Venus and Jupiter back in October. That's when I was hiking to work, and I stopped by the cathedral and I was, oh, look at this. It's a nice picture. One thing about observing while going to work is that I kind of forget I have to go in to work. I haven't been late yet, but this morning I was actually watching the four planets at Venus and Saturn really close together, Mars and Jupiter. And I look at the time, yeah, I gotta go in. Well, Saturn, yeah, the Enterprise visited about twice. The first one was probably the best scene of the movie in 2009. The Enterprise came out of warp in Titan's atmosphere and then rolls out and Saturn in the background, really nice. And then the bottom here, you have the Borg heading to Earth, take over the Earth. By Saturn, and the Enterprise behind it. Well, I'll just go quickly here. This is more there's Saturn and Venus together. And at the end of the month, you're going to have Saturn pull away. Venus is heading down behind that superior conjunction behind the Sun, Mars and Jupiter. Yeah, this is one of my favorite pictures taken from Cassini from the shadow of Saturn. You have Venus up here, Mars, Earth right here. This is a picture of that area. We have the Earth and the Moon. This was on the wave of Saturn event, July 19, 2003. I made a point of stopping the wave at Saturn. It was broad daylight, but it was just for a memento. Neptune, quickly mentioned in the first episode of Star Trek Enterprise, where the first Enterprise is testing the warp drive. It's going to go to Neptune back in 6 minutes. One day I'd love to see this. Neptune right now is right here. Can't see it right now. It's a conjunction. It's about a month and a half. But next opposition date is September 2nd. And it'll be a much better time to see it. about 30 AUs. It's the farthest planet. It's a Pluto planet anymore. It's that dwarf planet. Magnitude about 7.8. So you need an average telescope to see it, or binoculars in the very dark sky. And Triton, its moon, is the largest moon with a retrograde orbit. So probably it's been captured by from the center of Kuiper Belt. Kuiper Belt, speaking of, it was mentioned in Star Trek Generations, where the new Enterprise B, came out of space dock, and it's just good to be on Pluto and back. Ended up going farther out. So the Kuiper Belt, here it is, it's beyond Neptune. Its distance is about 30 to 50 AUs. And the mass is estimated about being 1/5 that of the Earth. Well, we talked a lot about Pluto because of all the information we got from New Horizons. I'll keep it very short so we can go on to the next one. Pluto right now is around Sagittarius. This is its path for the next few years. It's quite difficult to find it. It's at magnitude 14.2 right now. And if you want to wait, I don't know, 120 years, I'm willing to wait for that. It's going to be in Taurus and Gemini, much easier to find. The conjunction is, or was, just this week, so you can't see it right now, but wait till July 17th, it's probably taking up for it. This is a new Kuiper Belt object that was found 2 years ago, 2014 MU's 59s. It's part of the Hubble Space Telescope, and now the horizon is heading to that small object, and it's about 44 AUs away. And magnitude 26. Anybody have a big enough telescope to look for it? No? Oh, okay, me neither. So yeah, don't look for it. The Oort cloud. Okay, now I'm guessing here that the Enterprise B, the same as at the beginning of generations, probably made it around the Oort cloud. They went to look for refugees and bring them back to Earth. So it was a very quick trip, so I'm guessing they went about that far. It's also a sad scene where Captain Kirk was presumed killed. So this is the Oort cloud. It's about 2,000 to 5,000 AUs. Possibly could go up to 200,000 AUs, or about 3.16 light years. The remnants of the formation of the solar system. That's where you find all the nucleus for comets. And when the sun was created, probably might have been created within a star cluster. So part of these Oort cloud objects might be from different stars that were forming in the same area as the sun. So anything that can disturb an object, say the passage of a star or a collision between two objects, or even the gravity from our Milky Way, is probably enough to nudge an object and set it with the sun to make a comet. Speaking of comets, okay, well, Brian did a great presentation, so I'll just go right through this quickly. It was said Arcturus right here on January 1st. I saw it, I think it was January 4th, about right here. And in the coming days, we're going to have a great opportunity to find it by the handle to get bigger. And what else have I mentioned here? Yeah, okay. This is a comet that's heading out the solar system. I found that it's going about 46.4 kilometers per second, and that's slightly above the solar escape velocity. So if it's long gone, take a look in the coming weeks because you're never going to see it. This is a quick look at the solar system, or in Star Trek they call it Sector 001. This is just probably a look at it. Comparison of distances, 1 AU, 10 AUs, 100, 1,000 AUs, and so forth, all the way to Alpha Centauri. I love this one. It shows all the objects in the solar system. All the terrestrial planets, the gas giants, the Kuiper Belt, the comets, and the, I didn't quite the Oort cloud. The Oort cloud is way up here. Okay, we're gone. We're not coming back to the solar system. Now we're going to Alpha Centauri. In Star Trek, we mentioned a couple of times, it's where Zefram Cochrane retired in entered the warp drive. And it's also a little quote of Captain Kirk said, as a reply to questioning when he was held in the 1860s. When asked where he went, he said, I'm Little Green Man from Alpha Centauri. Beautiful place, you should see it sometime. Well, I hope we will be able to see it. Alpha Centauri is right about here. Can't see it from northern hemisphere. You have to go south to see it. It's a triple star, yeah. The primary star is 0.01. Secondary star is 1.3, and you have a fainter one, 11.1. 11.1 is Proxima Centauri. Technically, that's the closest star to our solar system because of its orbit brings it, technically closer to us. So if there was a planet and we were looking at the sun from there, you'd probably see the sun as a magnitude 5 star test with it. Wolf 359. This famous star system was a battle with the Borg, and Starfleet kind of got decimated, and the Borg headed towards Earth. You have the Enterprise here that showed up too late because of engine problems, and it's just a good year. So Wolf 359 is right about here, just southwest of Regulus. It's very faint. It's a red dwarf, about 3.5 magnitude. And it does have a stronger magnetic field than the Earth. There are no disks or debris around it, so probably no planets yet. And it's a very small star. It's about 9% of the sun's mass, which is the minimum to perform hydrogen fusion. So if you want to take a look at it, then you just find Regulus and go down right about here. It's a fairly good telescope because the magnitude is 13.5 to 33. The Tellurites, apparently they're from a star, or the fifth planet around a star called 61 Cygni. They're one of the members of the United Federation of Planets, founding members, along with, I think, the Vulcans and the Andorians and Earth. So where is the star? It's, you can see this right here. I need that all the way over here. Let's look at it the other day. It's a double star, yeah. Two times four stars. It's a 15th nearest star from us at 11.4 light years. And about half the mass of the sun, like 763 solar masses. Andorians. They are from, not actually a planet, but a moon right here, in orbit of a green planet that's in orbit around Saturn. Well, we know where to find it, be able to show it to us. We have a winter triangle, and here it is. We'll do some serious kind of sign up here. There's probably not a planet there due to the white dwarf just over here. It used to be a red giant, and probably was the environment between those two stars might not have been any planets to form. But you never know, we might find some, but right now there's nothing there. Fable. This was one of a really good episode. Fable is a neutral planet. It's used for conferences and all that. It was in an episode called Journey to Babel. The Enterprise brought delegates for a peace conference. The Fable here is right about here. So it's about 14.3 light years away. It's a binary star. A lot of stars in the galaxy are binary, or triple stars. And it's about magnitude 13.2, so it's one of the dimmest objects you can find 15 light years away, or within 15 light years. And the binary stars are both very small, they're only about 1.14 solar masses. Vulcan, this I was always curious to find out where in the sky is Vulcan. Well, this, according to Gene Roddenberry, is the creative Star Trek. It's in orbit around 40 Eridani A. There was some talk it might be around Epsilon Eridani. For some reason, I'll get to soon. It's not there. It's around 40 Eridani A. That's the best star system for it. So its distance is about 16 light years away, which makes sense. If we have first contact by the Vulcan, you want them to be in the star system nearby. It's a triple star system. It's magnitude 4, 9, and 11. And its age is about 5 or so billion years, whereas Epsilon is only about 400 to 800 million years, which is too young probably to form planets. So far, there are no planets that have been found around this triple star, but it does have enough heavy elements to actually create a terrestrial planet. So if there is a planet, well, hopefully we're going to find one. It would be nice. And if there is a planet and you're looking at the sun from there, you're going to see it as a magnitude 3.4 star in Hercules. Okay, this is interesting. This episode called Mirror, about a planet in orbit around 70 Ophiuchi. It's an exact duplicate of the Earth. I don't know, those are what odds of finding a planet like that. I might be able to get drafted by the Winnipeg Jets if I runs a RASC. Don't count on it. So this planet is identical to Earth, same circumference, density, atmospheric topography. Where is the star? It is right here. 16.6 light years away. There have been claims of a possible planet, but none have been discovered so far. It's actually close to a large star, which is right here. So in this area, about here. The large star, I just mentioned it because it's the second closest star, at least star system, to our own after the Alpha Centauri star system. Terranova. This is featured in the Star Trek Enterprise. It's the prequel series. It's, in the Star Trek universe, it's going to be the first planet to be colonized by Earth in about 2078. 200 people will lead the colonization. Our planet has 2 moons. I don't want to go there for observing. You know, 2 moons. We have another one right now. So where is it? It is right here. Easy to see. I was looking at it just a few days ago. This too is a binary system. It's a magnitude 3.4, so it's easy to find. It's very similar to the Sun. Mass 97%, radius 101%. So very close to what the Sun would look like if you were on a planet over there. And you actually, no, sorry, let me go back. Okay, so if you were looking at that star, you can imagine what the sun would look like at 19 light years away. Anyways, this was an interesting episode where they found Apollo. And when the Enterprise entered orbit, Apollo decided to hold the Enterprise with a force field in the shape of a hand. And when I was younger and I saw this episode for the first time, it kind of freaked me out. I saw this hand coming towards the Enterprise. What is this? The Pulse is easy to find. It's over here. The brightest star in Gemini, magnitude 1.1. It's evolving into a giant star because it's exhausted all its hydrogen in its core. It's trying to work alien now. And there is a planet that's been confirmed around there, Pollux B. So when I saw this, I'm like, oh, this is interesting. This is probably the closest planet to us. That's both in our universe and in the Star Trek universe. Capella. This is from an episode called Friday's Child. The Enterprise visited a planet, Capella 4, fourth planet, another one planet. We had a showdown with Klingons on the surface and just outside the Capella system. Capella, well, we don't know where to find it. It's the brightest star in the weekend. It's circumpolar. You can see the best it's probably overhead by now. And you can see in the summertime, if you're doing some observing in the summer, you just look really low in the north, You see this really twinkling object. A lot of people think it's a plane instead of a UFO. I've had people ask me, what is that twinkling object? Really looks really yeah, it must be Capella. Capella is 42.8 light years away. And it's actually a four-star system. 2 pairs of giants, and the second pair are red dwarfs. Around magnitude 13.7 from the red dwarfs. And it's part of the Halley's moving group. It's an area of stars that are moving in the same direction. I'm not sure if Capella formed in that same area of the cluster, but at least it's been detected they're moving in the same direction. That's our. I don't think we've seen a visit to that particular star system. We've seen aliens from that planet. I mentioned Mizar because this is one of my favorite double stars. When I have my nieces and nephews over, they want to look through my telescope. I show them Mizar and I try to get them to resolve the Mizar A and B. And then I move over to Elvira, and they just love looking at that because I told them that's a blue bomber star. And they're wondering, why? What do you mean a blue bomber star? I said, well, look at the eyepiece. Oh, it's blue and gold. That's really nice. So Black and Mizar, this is actually a 6-star system. You can resolve Alcor and Mizar probably naked eye if you have a good vision. With a telescope, you can separate these 2 stars, but these 2 stars themselves are also binaries. I don't think you can separate them. Gamma Triangulum. This episode is famous for all its casualties. I don't know what famous is. It's kind of tragic. I'm thinking, what is going on? Why are there so many people being killed? Is it the color of their hair, their eyes? No, they're wearing red shirts. So if you're going to be in a Star Trek episode, don't wear a red shirt. So this planet, or star, is located right here in the triangle. It's a decent bright star, magnitude 4. And if you look at it properly with binoculars, you might think it's a triple star system. It looks like a triple, but it's really a line of sight triple. There's no relation between either one of them. It's a young star. It's about 300 million years old. So far, no debris disk has been, actually a smaller debris disk has been detected, but no planets, at least not yet. I know where the Klingon moon world is, and it's around Omega Leonis, which I'm going to get to in a second. But Kronos is a home world of the Klingons. They used to be the enemies in the original series, but now they're allies in the next generation. After the explosion of their moon, which is very early in Star Trek 6, this caused a catastrophe in the Klingons ready to talk peace. So the famous Klingons are, of course, coming to war with this generation. So, Omega Leonis is right here. I thought it would be, a really impressive star for a Klingon homeworld. Had a big regular system. It's right here, very faint. It's a double star, magnitude 5.9, 6.5. It's close to the ecliptic, so it's often occulted by the moon. So you see the moon getting close in that direction, you could probably look up and it's going to occult that star and have a look at it. It's easy to find. You just find it about southwest 10 degrees from Regulus. The triple homeworld, everybody's favorite little pets. As you can see, Captain Kirk is really enjoying them. They were featured most prominently in 2 episodes, Trouble, the original series, and Deep Space Nine, one called Trial and Tribulation. That was a good time travel episode if you've ever seen it, you know what I'm talking about. The Tribbles were mortal enemy of the Klingon Empire. I don't know why they look so cute. They were annihilated by them in the 21st century. And where do you find the star? It's about right about here. So polar Castor as the eyes, and you have Iota Geminorum as its nose right there. So it's about magnitude 3.7. It's fairly easy to find. Right now, it's a giant. It's, for all its hydrogen, it's not burning helium. And it shines very brightly, about 52 times out of the sun. That's all the information I found about it. Red alert. Okay. Gamma Hydra. This featured an episode that airs where Captain Kirk and a few of the landing party aged rapidly. Where do you find it? Right about here. It's really low in the sky. It's below Spica. So it doesn't get very high in the sky. It's magnitude 3, so you should be able to find it. The thing I do like about Gamma Hydra and many of these stars, it's featured in the Brazilian flag. So Gamma Hydra would be the one right about here. This represents the sky over Rio, November 15th, 1889. How about Back to the Future? No, that's 1885. So about 8:30 in the morning. So this Brazilian flag represents the sky over Rio. And these are all the stars in the sky in the southern hemisphere. And they represent different states of Brazil. The Romulan Empire. I was looking for Romulus, and I just couldn't find it. The only thing I found was Achenar, if I'm pronouncing it right. And it's considered the home world of the Imperial Romulan Senate. This has confusing information about Romulan politics. I didn't get into it. But anyways, I just have to concentrate on this one. Achenar or Alpha Hebridan. You can't find that object here. It's a southern hemisphere object down here. It's very bright. It's magnitude 0.46. And bright star in the sky. Very bright, about 3,150 times more luminous than the sun. And that too is a binary system. And it's the least spherical star in the Milky Way that I could find. It is rotational speed of 250 kilometers per second. And for comparison, the sun rotates at about 1.9 kilometers per second. And due to that speed, it bulges up at the equator. So the equator is about 56% wider than the polar diameter. Ceti Alpha 5, or Alpha Ceti, or Mencar as we say in our universe. It's something that when I found this object, I'm like, wow, okay, this is my favorite original episode, Space Seed, and movie Star Trek 2. And this is where Captain Kirk is Khan years later on Star Trek 2, the Revenge of Captain Kirk. So this would be Mencar, with, of course, the Enterprise fighting the Lion. Where do you find this star? Let's see. Send us right here. 249 light years away, magnitude 2.54, so it's fairly easy to find. It's twice the mass of the sun, and about 89 times big. It's at the end of its life. It's done burning helium, now it's going to burn carbon. It's going to become unstable, and it's going to shed its outer layer, become a planetary nebula. Omicron City, just next door. It's also known as Mira. It's featured in a couple of episodes of Star Trek. One of the original series that I want to finish. So Mira is about right here. It's also a binary star, about 300 light years away, and it's famous for its being the most variable star in the sky. It can vary in brightness from magnitude 2.0 to 10.1. And it becomes naked eye at 2.0 for about 1.5 months. before and 2.5 months after its peak. So these are the dates of the next maximums. March 5th, you can see it, but is it going to be behind the sun? I'm not sure. Yeah, okay, I can't see for a map. So the Pleiades, enterprise of mapping planets and Pleiades in one of the episodes. And we all know where the Pleiades are. It's over here in Taurus. It's a famous cluster. It's about 444 light years, magnitude 1.6. And it's very young. It's only about 100 million years old. And it has a mass of about 800 suns. Right now it's moving towards the feet of the Big Dipper, so it's moving to probably in this direction. And it looks like a little dipper. Every time I show this to, say, my niece and the nephews, they're looking at my binoculars, oh, it's a little dipper. Almost. And you get people interested in astronomy as well. Right now, there's a possible star that's, a planet that might be discovered around HD 23514. I don't know which one it is. One of these. This guy, I do like this picture of the Pleiades. It's an X-ray. It's really different from seeing it like this. This is a really nice picture. Look at it next to each other. Rigel is mentioned so many times in Star Trek. I'm not going to mention everything. It goes from Rigel 1, 2, 3, 4, 5. It's also the first star system the Enterprise visited in the prequel Star Trek Enterprise. So this is Rigel. Of course, we know where to find it. It's right here. I find it very impressive, this picture. This is Rigel compared to the Sun. Rigel is about 79 times the size of the Sun. Probably go past the Earth's orbit. It's 31 times the mass, and it's the closest supernova candidate to Earth. It's heading for a Type 2 supernova. So when it does go supernova, it should be quite a show. So Rigel is up here in the Hertzsprung-Russell diagram. Very bright as well. It's 120,000 times out of the Sun. Delta Orionis, or Mintaka, visited by Enterprise D in Next Generation, third planet Mintaka 3. Very nice episode. This is a point of view of the inhabitants of that planet as they see an advanced race come to visit them. They thought they were seeing gods. They made Captain Picard here as a god and called him Picard. So here it is, the rightmost star in the belt of Orion. It's about 1,200 light years away, magnitude 2.2, and it's a triple star system. So it's a subgiant and a main sequence star. The cultural significance of this star, well, not the star, but the belt itself. In Spain and Portugal, they call the three stars Las Tres Marinas, which means three Marys in Spanish. And for Christians, the three stars represent the Magi, or the three wise men, Caspar, Melchior, and Balthasar. They're heading to Bethlehem, which is represented by Then this was the first destination of the Enterprise D, the pilot episode of Next Generation. Deneb 4, the fourth planet around Deneb. So Deneb, of course, we all know where it is. It's part of the Summer Triangle. Altair and Vega. It's a white supergiant, and the distance is hard to determine, but it's about 2,600 light years away. That impresses me because when you look at Vega, and it's almost as bright, but Vega is really close. It's about 20, 25 light years away, something like that. And you have Deneb, which is so far away, almost the same brightness. Diameter is about 200 times that of the Sun, and it extends to Earth's orbit. 19 passes, and it's now cooling and expanding. It's near the top of the Hertzsprung-Russell diagram that I showed you earlier. So, yeah, Deneb is right here. The North American Nebula, it's thought to be energized by the radiation from Deneb. Okay, now we're off to the center of our Milky Way galaxy. Apparently, there's a planet there called Shakrali. That's the main story in Star Trek 4. And the center of the galaxy, Star Trek anyway, is protected by an energy barrier that the Enterprise crossed. I found this interesting. Shakrali is an allusion to the name Sean Connery. Yeah, some people have a good sense of humor. He was actually considered for the role of Spock's half-brother in that movie, but he was busy filming this Indiana Jones and Lost Crusades. So he wasn't available for the movie. So here's the center of our Milky Way. We have a center, okay, the colors don't come out very well in the projector. It's about right about here, or here. So it's at the tip of the Sagittarius, and I tell you, this part of the Milky Way is best seen from the Sprucewood Star Party. Apparently, it's better in Arizona, but no, I don't think so. I'm the Sprucewoods and have a look. So yeah, there's a whole bunch of objects to look at there. I'm just going to talk quickly about the black hole that's believed to exist at the center. Are we doing for time? Oh, okay, almost done. So at the center of our galaxy, apparently there's a massive hole. This is a diagram. You look at the stars and going around, they just zip right around this area. So there is some kind of gravitational pull just making them slow each other like that. So that's evidence of the black hole. This is a X-ray version of the center of our galaxy. Here's a look at a galaxy with superimposed with different areas in Star Trek. In Star Trek, they divided the galaxy into 4 quadrants. There's Alpha Quadrant, Beta, Delta Quadrant, Gamma Quadrant. Delta Quadrant is featuring Voyager. So you have the Kazon space, Borg space, which extends, I think, around here. So we're still safe for a while. Right here. So you have the Romulan Empire, the Klingon Empire, you have the Federation, which extends all the way around here. Mostly Alpha Quadrant, a little bit of Beta Quadrant. And of course there's Dominion space, which is featured in Deep Space Nine. There's a wormhole going from about here to here. This is the Alpha Quadrant and the Beta Quadrant. So yes, I have a test at the end, so please study the star system. Right? The sun is about right here. Romulan Empire, Klingon Empire. We had a good look here. Okay. The galactic barrier. So yeah, in Star Trek there's some kind of energy barrier around the Milky Way. I don't know if there is one or not, but instead I'm going to talk about globular clusters, at least one of them, M15. So globular clusters are a bit different from open clusters. Open clusters are, let me go back here. Open clusters are in the disk or Milky Way, whereas globular clusters are in the halo. So the halo itself, I don't have a three-dimensional picture of it. It's like a sphere around the Milky Way, and that's where all the globular clusters are. 150 of them, like that. So M15, I do like it. It's a really nice object. It's right here. It's in the constellation of Pegasus. It's about 33,600 light years away, 92.6.2. And it's a really old globular cluster. So all the clusters are really old. This one's about 12 years old. It has about 100,000 stars, including variable stars and pulsars, and it's densely packed. I'm not too sure why. It's either gravity or there may be a black hole at the center. So this is a really nice object to look at. It's one of my favorites after M13. I don't know, M13 always attracts me to look at it first, but I think that M15 is a really nice one too. Andromeda Galaxy, M31. The Enterprise was heading for that galaxy, but turned around. It's an episode by any other name. Kelvin's hijacked the Enterprise, wanted to go back to their home world. But I think Captain Kirk used his charm or something and got them to turn around. 131 is easy to find, it's right here. You can use Cassiopeia to find it. You use the V on this side and just point this way. I prefer taking the 3 stars over here. I take the middle one, go up to, it's easy to find. And it's one of the farthest objects you see with your naked eye. Unless you can see M33, which is a little way up. And Andromeda is heading for us in 3 billion years. So Sheila could do time travel. Go out on the rock. I can go this is great. Try to go in Galaxy. Visited by the Enterprise D by a freak accident. Testing the warp drive. Something went wrong. One light year away, we ended up in the far side of 133. So I was mentioning that I like looking at the 3 stars here to find M31 because I could go back to this star and go back down the same distance and find M33. I've seen it naked eye, like in Spruce Wood. And this is, yeah, I guess it's the most visible object you can see with your naked eye. And there's some evidence that these 2 galaxies, 33 and 31, are linked together just because of some hydrogen gas that is flowing between the 2 galaxies. This is a beautiful shot taken by Sheila. The outer rim, almost at the end of our journey. This is where the Enterprise ended up being after they stopped by M33 and tried to go back home. Rooms where the outer rim, where it's either what they call the beginning or the end of the universe. Well, I don't know exactly where to look in the sky for that bit. So I just took this picture. This is the most awesome picture I've ever seen in astronomy. It's taken with a Hubble telescope. And it was made with, using about 841 orbits, about 50 days of gathering light. And this is what they came up with. An area of the sky, which is about 1/10 the size of a full moon. Every little object you can see here are galaxies, except probably a few stars here and there. I think this is a star. Anyhow, yeah, there are 10,000 galaxies just in this image. It's incredible what's out there. So this is the faintest object, or even the farthest object detected so far, at least in July 2015. It's been detected to be about 13.2 billion light years away. And then these are its coordinates that I picked out, and I figured out it's at the northern tip of the Buoys. I hope I got this right. And with James Webb being launched in 2018, hopefully we're going to see things even farther out. There you go, these are the objects that we looked at least that we can observe. What do you want to do with a list like that? Well, you could look at them, record them in your logbook, say how you found them, what it looks like, features, surrounding area. Here's astrophotography, and we'll take a picture. It's going to take say a picture of a star. Now, it's not too impressive, just, zoom out, take a picture of the area. Or if you like sketching, you can sketch that too. And suppose you come back to me and say, hey, look at this, Mark. I observed all these objects. What do you got for me? Now, I might get you a certificate signed by Captain Kirk or Captain Picard. That's it. The end of our journey. Yes. Cows are important in Star Trek. There are many times. Commander Data has that name. Do you have questions?
Well, you're going to have to start the Star Trek to the handbook.
Yes, okay.
And then you get a nice little Star Trek bag. Well, we don't have any questions. They'll be saved for pizza, but Mark, we'd like to give you a little piece of the universe as well. So thank you very much for your entertainment tonight.
Thank you.
the end of our meeting, we'll go over to Boston Pizza for those that want to continue the association with us. And we'll see you next month in February.